Okay, here we go with combination circuit. So I suggest right now take the notes. I give you RT, just a little method of solving RT. Take your notes and try to work this out. Pause the video, just write down the circuit. See if you can work it out for yourself and take it from there. And now I will continue. So we have RT solved, so I gave you the answer, 735.59 ohms. So, sorry, 787. So what we did was we just did the reciprocal here, so 1 over 750 plus 800. So don't forget, we have to change our values here into ohms. So convert the kilo ohms. I got 1.4, 0.8. So this is 800 ohms. This is 1400 ohms. Here we have 52 and 750, so we're good there. So these two are in series. So we have to add these two up, the 800 and the 750, and that's what's going on right here. And then once we add these two up, they become one resistor. And then we calculate for the sum of these two plus the 1400. So, and then we just take the reciprocal of that, and we end up with this number. So that deals with the first part of the circuit. So as far as the circuit is concerned, so what we have is so what we did was the 750 and the 800 right here, that combined because they're in series to 1550 ohms. And then, so what we have now is a parallel between these two. So the next step, so the first thing we want to do is combine them. And then we want to deal with this end of the circuit as a parallel. And that's what this is right here. So between the two of them, we deal with them as a parallel, and they combined to 735.59 ohms. So this combined to R3 and R4, which is R3 and R4. And we combine them now, 735. So this is R2, R3, and R4. So it's this one and then this two. So now we have a series circuit, and we can solve for the amperage. So we got 52 ohms, which is going to be added to the 735, which is the second step. So step 1, add these all up, get this back end accounted for. Step 2, once we have this value, we can add the series circuit together, and that comes to 787. We'll just go to 2 decimal places, 0.59 ohms. And that gives us our RT. So we can move ahead now to our IT and our PT just to finish it off, and then we can start solving for all of our drops across all the resistors. So we move along, and what we have here, so IT, and again, pause the video so you can move along. I've tried to make it so it just comes together in pieces here. So IT 0.1142 amps, PT 10.27 watts. So what we can do here is we want to see the voltage drop across that first resistor. So we can use this first resistor is going to see the total current in the circuit. So we have 0.1142 amps times 52 ohms, just straight Ohm's law, gives us 5.92 volts. That's going to get dropped across this resistor. So if we take the source voltage and then we subtract the voltage that got dropped across this resistor, we end up with 84.08 volts. And that's what the rest of this circuit is going to see. So we got the parallel here, and then this voltage coming across these two resistors, or feeding this part of the circuit. So it stands to reason that we should be dropping the total voltage across this resistor, but the voltage here is going to be split between the two. And you always want to watch, again, look for the relationships. If you have 750 ohms and you have 800 ohms, what you should be looking for or thinking to yourself is, what is the relationship? What's the ratio? If I'm going to drop and again, look at the rules I have, that's in your history of ratios document. I have that sitting in there. So you should be instinctively telling yourself, well, there should be more voltage drop across this one with this one. That's always what you're looking for. So 84 volts dropped. Now this is just a backwards function for the current in R1 to this one. So literally it's being just worked in reverse. 592 volts, and again I've just set up straight Ohm's law here. So you're literally just going backwards from one to the other. So the current in R1, 0.1142. So again, pause it if you want to move forward, and here we go. So now we have all the values, and again what you want to watch for right here is your voltage drop, and notice the ratio in here. So I put down all the values, so your voltage drop across R2 should be the complete voltage in the circuit. R3, now what you want to notice here about the current in R3 and R4, they should be the same, because this is a series circuit in here. So the rules to series circuits is they're going to see the same current, and that's how we're going to solve for the voltage drop, because it's common to the two. So we solved for the current here, the total current, R1, and then R2 is going to have its own current. It's going to have the complete voltage, but it's going to drop the complete voltage. And then R3 and R4 are going to see this voltage, but they're in series, so they're going to share the same amperage here. So what you'll notice is R3 and R4 have the same current, and we're going to use these two values and we're going to plug them in right here. R3 and R4 are going to have the same current. So when we're solving for these equations, those are the things you want to sort of notice and pay attention to. Don't just input values blindly. So, and you'll see here again the relationship, 40.65 volts for the 750 ohms, and it's dropping a little more voltage for the 800. Makes sense. We're only 50 ohms out, so it's going to be just a little fraction there. And then the power, well, once we have everything accounted for, all we're going to do with the power is just use the values that we've already solved for. So the P in R1 is going to be the voltage drop across R1 and the current in R1. So you're going to use the voltage drop in R1, or the VD across R1 and the current in R1. The power in R2 is going to be the voltage drop across R2 and the current in R2. So the VD across R2 and the current. And then same going for the power in R3 and the power in R4. So just to recap that here, these are sort of the values that you're looking for. And just to pay attention here, just like again, don't calculate blindly. Always be looking for those relationships. And the numbers will just sort of come out as you should be able to anticipate just by looking at the numbers and basically following the rules. So I've just highlighted a few things, just some common values here that are reoccurring through the calculation. Now, to tie it all in, the significant figures and the scientific notation, I think I've given you some exercises on those files there. So the current in R1, well, what are the significant figures, and what is it in scientific notation? So that would be this value right here. And then the current in R4, just to change it up, the significant figures and the scientific notation. I'll let you pause the videos if you like, solve for that. And what we have here is significant figures. We have 4, which are just on the tail end here. Scientific notation to 10 to the negative 1. And again, when we have, this is your 10 to the negative 1, negative 2, negative 3, so forth. Significant figures for R4, there's 3 of them. The 0 is not being counted. And then the scientific notation, 5.42 times 10 to the negative 2. And that's it for the combination circuit. So if we move on to surface area and volume, I went through the circle, the method of exhaustion, and all that kind of thing, just to sort of elaborate on sort of the relationship of the shapes. So if we deal with surface area and volume, to calculate, say we got a can of Campbell's soup or Pepsi or whatever your beverage of choice would be, we have a top, we have a bottom, and then we have the body of the can itself. So the surface area and volume, the formula for it is 2 pi r squared. Now this is surface area. Volume is expressed, so area is expressed in square, because we're not dealing with depth, we're just dealing with surface area. Volume, we're dealing with cubes, we're dealing with a third dimension there. So surface area is basically all we're counting for is the area at the top, the area of the circle at the bottom, and the body of the cylinder. So what we have here is 2 times pi r squared. Now pi r squared is the area of a circle. So you have pi r squared here, this would be the top, pi r squared here. So this is 1 times pi r squared, 1 times pi r squared, here's your 2 pi r squared, plus the height times 2 pi r, 2 pi r being the circumference. So if we took the body of this and sliced it right in half, this is the cylinder, and we just sliced it in half and we peeled it open, you would end up with this rectangular shape. So here's the height, right here. And here is the, so this then, this edge would be the circumference of a circle, also known as 2 pi r, or 2 times the radius times pi. So we have, so we're just adding up area here. So this is area, right? So 2 pi r, the circumference, times the height. These two, the top and the bottom of the cylinder. And that's what we're looking at here. So if we have an example, if the radius is 4.5 centimeters, the radius, right, being from the center out, and the height is 14 centimeters, that's the height right here. All we're going to do basically is plug the numbers into this formula. Pi being, you have that on your calculator, you can punch that in however you like. If you could actually just punch in the pi function and carry over all the decimals, you'll have a more precise answer. So if we just basically plug the numbers into this formula, it's relatively simple. 2 times pi times 4.5 squared gives us this value. 14, plug it all in there. We have this value for a total of 522.81 centimeters squared. Similarly, for the volume, now we have pi r squared. We're not dealing with the 2 anymore. We only need one of the values, and we're going to multiply that, so you have this total area, and it's going to be multiplied by the entire height. And that will give us our volume, the 3-dimensional volume. So we're going to take pi r squared, which is just the value of one circle, and we're just going to multiply it by the height. So again, we'll take the exact same values, plug it into the formula, and away we go. And don't forget to express it, the volume, in centimeters cubed and not centimeters squared. Just sort of, that's the one thing, and when I have students that make those little mistakes, they just miss this minor detail here. And it's one little note here. When we deal with pi r squared, that is not equal to pi times r squared. It's pi times the radius squared. That's is another place where I get little hiccups in the calculations, usually just calculator error. So just be careful of those little nuances in this calculation, and everything else is pretty straightforward based on the previous lesson. So here I have the answer to project 6. The wiring diagrams, I told you guys to, well, if I didn't, either way, scratch these 2 posts out. Oh, I forgot to draw the lines over there. Those are the bumps, throw those bumps in there. But here we go, cap off the neutral. That's under 4-022, several 2. Don't forget to draw in the boxes with your ground tabs on there, neutral, your hot, and your switches. Everything is coming into this box as central. So that's the key to that one. So I'll wrap up this video, and I will continue the next 2 in the next video. I'll see you right away.